Now that we've talked about R and R2 and R3 and generally Rn, let's talk about how we measure distance in these spaces. So let's start with just the ordinary set of real numbers. Okay, R, R1 if you prefer, one-dimensional set of real numbers. How do we measure the distance between two real numbers? So let's say we have right here we have x1, and over here we have x2. And we want to measure the distance between them, which I'll call big D. So we kind of intuitively probably know how to measure distance. If I'm 3 feet away from a car and I keep walking and now I'm 8 feet away from a car, how much distance did I travel? Well, from 3 to 8, that's 5 feet, right? You just subtract the numbers. Bigger number minus smaller number. So distance is bigger number minus smaller number. And if you don't want to keep track of which number is bigger and which number is smaller, you could just throw it inside some absolute values. And that'll make sure that we always get the positive distance. Okay, so to find the distance between two real numbers, you just subtract them and take the absolute value. How about R2? So R2, we're going to use some pretty familiar ideas, and you are probably already familiar with how to find distance in R2 using the distance formula, but let's rederive it because it's going to help us when we go to R3. Okay, so say I have 2 points. Say we have x1, y1 here. And another point, let's call it x2, y2 over here. And I want to measure the distance d between these points. All right? So the trick here is to construct a right triangle. Because once we're dealing with a right triangle, we have lots of rules that work with right triangles. Specifically, what we're going to use here is the Pythagorean theorem. Notice that each one of these legs of the right triangle is only moving in one dimension, only moving in one direction. So the horizontal leg here is only moving with respect to x, right? The y is staying constant along that leg. So to measure the distance here, we're just going to use our one-dimensional distance formula, okay? So I'm going from x value of x1, so that's x1, to this x value over here, which we could see because it coincides with this point, is x2. And so the distance is just absolute value of x2 minus x1. Okay? And same thing with my vertical leg. It's just the y value that's changing. I'm just changing from here to here. So from y1 to y2. So just changing in one dimension, I just subtract the two numbers and take the absolute value. So I get y2 minus y1. And now I have 3 legs of a right triangle. So I can use the 2 or 3 sides of a right triangle. So I can use the 2 legs of the triangle to find the hypotenuse. And so, by the Pythagorean theorem, the hypotenuse squared is equal to the sum of the legs squared. So absolute value of x2 minus x1 squared plus absolute value of y2 minus y1 squared. Okay. Now, couple observations here. First off, because we are squaring everything, we no longer need the absolute values. Right? Whenever we square something, it turns positive. So we don't need to make sure it's positive beforehand. The square will make sure it's positive for us. So I'm going to drop the absolute values. Let the square do the work for us. And so that's one less thing we have to think about. The formula looks a little nicer without the absolute values. Okay? And second, what we really want here is d, not d squared. So I'm just going to take the square root of both sides. So d is going to be equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Now, normally when we take the square root of both sides of an equation, we need to be very careful and make sure we consider both the positive and the negative root. This symbol, remember, we call it the square root symbol, but it's really the principal root symbol. Generally, every number has two square roots, a positive and a negative. This symbol means the principal root or the positive root. If we want the negative root, we have to put a negative in front. And generally, when we take a square root, we need to be cognizant that there are two of them. But in this case, I don't need both of them. I only care about the positive root, so I can leave the symbols off entirely because that means positive root already. And I know I want the positive root because I want a distance. Distance is positive. Okay? So I can leave off the negative just because in this situation, it's not physically relevant. All right? And so we have a formula for r. We have a formula for distance in R2. I want to emphasize that this really is an extension of the distance that we found in one-dimensional space. They don't look especially similar, do they? But in fact, if we rewrite distance for r here, they are similar. And the key here is realizing that there's another way that we can write absolute value. Okay? So to see this, consider that what do I get if I take the square root of -2 squared? And here the square is inside the square root. That's very important. Okay? Well, -2 squared is +4, right? Because I square the negative. And this symbol always means the positive root. So the positive root of 4 is a +2. Notice the square root and the square, they didn't just cancel, did they? And so you got to be a little bit careful here. Square root and square, they're not perfect inverse operations. If this was a +2, they'd cancel. But generally, they do not, because the square root symbol gives the positive root. So generally, what we get here, if we take the square root of some number, let's call it x, and we square it, then what we get is the absolute value of that x. It always spits out the principal root, the positive root. Okay? Which means there's another way to write an absolute value. We can also write this as the square root of x2 minus x1 squared. It means exactly the same thing. And writing it like this, you can see that there is definitely a similarity between our two-dimensional distance formula and our one-dimensional distance formula. We're going to see this pattern continue. Let's see what happens when we go to R3. Let's draw our three-dimensional space. And let's imagine 2 points in this space. Say x1, y1, z1 here. Let's do x2, y2, z2 up here. And we want to measure the distance between these. Okay? And let me just draw give you a little bit of context here by drawing some dotted lines. I'll just draw it down to the XY plane. Okay, my point here is that if I just draw it in 2 dimensions like this, embedded in 2 dimensions, it looks like it's part of the YZ plane, but it's not. This point is kind of pulled forward a little bit. Okay. So I want to really, again, kind of draw a triangle here. It's kind of like that. Okay. Okay. Now this vertical leg here, I can easily find because the only thing that's changing here is the Z. I'm just going straight up and down. And so I want to go from this point here, the Z value of this point, it shares the same Z value as this point. So it's going from Z1 to this point, which is Z2. So this distance here is the absolute value of Z2 minus Z1. But for this triangle here, that's a little bit trickier. I'm sorry, for this line here, that's a little trickier, finding the distance here, because here, this line, it's not just one distance that is, or one variable that's changing, okay? Both the x and the y variables are changing here. So the x, I kind of go this way a little bit, and the y, I go this way a little bit. Let me maybe start from the y first. Okay, hopefully that makes sense what's going on there. Let me tighten up my lines a little bit here. Okay, hopefully that makes sense what's going on. This triangle here is a right triangle parallel to the XY plane. Okay. And so I'm going to call this distance here, let's call it little d. I'm going to make it green. There we go. Little d. And so drawing it like this, I could see that this distance here, this change here, I'm only changing the x. I'm going from this x to this x. This further x is the same as this x. So I'm going from x1 to x2. So absolute value of x2 minus x1. And here I'm only changing the y, going from this point to this point. So that's absolute value of y2 minus y1. Okay. And so now I have a triangle here. I can find that little d using our distance formula for two-dimensional space. Okay, or just the Pythagorean theorem if you want. I'll have x2 minus x1 squared plus y2 minus y1 squared. Again, I could drop the absolute values since I'm squaring them. And I'm taking the square root. I want the positive root because little d represents a distance. And I could also see big D, again, using the Pythagorean theorem. And let me emphasize this is a right triangle here. Okay. Big D is the square root of the one leg squared, so that's little d squared, plus the other leg squared. The other leg has length z2 minus z1 squared. Okay, but we know what d is. D is the square root of this, so d squared would be x2 minus x1 squared plus y2 minus y1 squared. So if I plug that in, then I get for d squared is x2 minus x1 squared plus y2 minus y1 squared plus, and then my z, my last component here is z2 minus z1 squared. And so that's the distance formula for R3. And we could see a pattern here, right? For one-dimensional space, just the square root of the difference of the numbers squared. For two-dimensional space, it's almost the same thing, but I do it for each component of the two ordered pairs. And then I add them together, then I take the square root. Okay? For R3, well, in R3, I have an additional component. So I find the squared distance for each of the components. I add them together. I take the square root. Okay? Hopefully this makes sense. I realize it can be a little bit hard to parse because, again, I'm working in three-dimensional space, but I've embedded it into a two-dimensional surface. Your screen is a two-dimensional surface. But hopefully you can kind of make sense of what's going on. This triangle here is going straight up and down, but it's kind of at an angle in the horizontal direction, right? So it's going straight up, but it's not flush with the YZ plane, kind of at an angle. And this triangle here is parallel to the XY plane, which is why I drew this other triangle. It's the same triangle, it's just lower down. And so it's flat. It's flat on the XY plane. Okay? If we go to higher dimensions, the same pattern holds, so it's harder to visualize. So in R4, following the same pattern, the distance between 2 points x1, y1, z1, w1, and x2, y2, z2, w2 is d equals the square root, and all I do is I take the difference, the squared difference between each pair of coordinates, and then add them together. And I take the square root. And more generally, Rn for any number of dimensions n. Could be 2 or 4 or 5 or 7 or 103. The distance between 2 points and let's call our 2 points A and B. So I'll call point A, and it has coordinates A1, A2, all the way to AN. And B, and the components of point B is B1, B2, all the way to Bn, is D equals square root, and just subtract the corresponding components. So the first coordinate in B minus the first coordinate in A squared, plus the second coordinate in point B minus the second coordinate in point A squared. And keep on doing that until you get to the very last coordinate. Since we're in n-dimensional space, the last coordinate will be the nth coordinate. So subtract the nth coordinate, bn minus an squared, and then take the square root. And that's generally the distance formula for n-dimensional space.